bivalves developed enabled them to store their life history within their shells, reflecting the environmental and the climatic changes. They have been used as a scalochronological tool to resolve the climatic records in geochemical studies. But what else besides the influence of the surrounding conditions could affect the bivalve's growth? Would it be possible that symbiont-bearing bivalves grow faster than the non-symbiont ones, even if they grow in the same environment and in the same circumstances? The ongoing research is initiated to solve this question by studying rudist as a symbiotic bivalves and comparing it to oysters as a non-symbiotic control group. But first, let me introduce these two groups, starting with rudist. There are sessile epiphoinal bivalves that have developed with vertical incrementally growing asymmetrical valves. The lower valve is always attached to the substrate, showing a conical to cylindrical shape with an operculiform upper valve. They appeared during the late Jurassic and flourished throughout the Cretaceous, occupying the shallow tropical environments that were characterized by sea surface temperature of around 30 degrees Celsius in the subtidal zone above the thermocline. Their dominance within the tropical zones have been presumed to hinder the growth of other immobile organisms during the Cretaceous period, like the zooxanthellate corals. Rudists could secrete their shells with rhythmic patterns of both tidal and daily increments, their growth rate synchronized with the surrounding conditions of water energy, depth, temperature, and light. But these are rudists, and they have always something unique to show. Besides the ecological factors, photosymbionts had played an important role in the shell precipitation and morphology that will be reflected in their chemical composition. Oysters are also epiphoinal bivalves that are characterized by concentric lines marking the shell growth increments from the ligament towards the margin. I'm studying 4 bivalve species of 3 rudists and 1 oyster that have been collected in live position from the Upper Cretaceous Samhan Formation in Oman. The exceptional preservation of the oysters and the rudist from this locality makes them an ideal target for the current study. The growth rate of the rudist species has been a topic of several earlier studies, showing that they tend to grow from 1 to 4 cm per year. But this rate could vary depending on the ontogenetic stage of the specimen. In this work, I'm aiming to test the individual growth rate and estimate a lifespan for the 4 species, and establish a comparison between the growth rates of these bivalves with respect to the presence or absence of symbiotic interaction. Measurements of stable oxygen and carbon isotopes have been obtained as an essential methods in this work, but prior to sampling, I have checked the shell composition and the shell preservation by different methods. I prepared petrographic thin sections for the Raman spectrometry analysis of the shell mineralogy. Then I used the scanning electron microscopy to investigate the shape and the microstructure of the shell. And to identify the elemental composition and their distribution, I used the energy dispersive X-ray spectrometry. This has been done to obtain a realistic isotopic record, as it's necessary to have a pristine shell fragment, which is free of any diagenetic overprint, as it's shown by the consistent fine bands. This shell part is mostly unaltered and show high calcium content. Yeah, I know that some of you have noticed the silicification in red, but I showed it just to say that even when they develop, these crystals are very small and so localized that cannot invade my growth counts, and they can be avoided during the isotope sampling. And if we go back to the first 2 pictures, we will notice that the cementation or the metastable mineral replacement was dominant in the body cavity and the outer margin of the outer shell layer. So the pillars of the lower valves in Turritis sanchez and Vexanites are a valuable scalochronological profile for high-resolution sampling, as well as the compacted outer layer in the oysters. Statistical analysis and chemical measurements of the shell isotopic composition of stable carbon and oxygen in previous studies show that the external bands of rudists are of annual origin, and each species would have different growth rates. Based on that, I will carry out a cross-validation of internal increment counts to assess their matching with the outer growth bands, assuming that each internal line is corresponding to one day. But there is never enough time to talk about rudists, so today I will show the preliminary results of one rudist species. And let's take Turritis senchesi as an example. Counting have been done through the finely banded pillars of this specimen, and I used for this the petrographic thin section and the fluorescence microscopy images. The increment number amounted to 430, with no significant variation in width. This could indicate that the growth rate was steady with an average increment width of 29.51 micrometer, with an estimated growth rate of 5.07 centimeter per year. Then I sampled the specimen for the stable isotopes measurements using the micromil for high spatial resolution sampling, following the fine growth bands within the pillars. But to make sure that my supervisors will not declare themselves bankrupt after this project, I sampled only half of the counted increment. Where 280 tracks were placed as a time series transect, and each drilled sample comprises of 2 tracks. The oxygen isotope ratios ranging from -6.93 per ml to -4.23 per ml, and the carbon isotope ratio ranging from -0.82 per ml to 2.63 per ml. And then, from the oxygen isotope value, the paleotemperature has been calculated, showing a maximum value of 40.4 Celsius and minimum value of 29.6 Celsius. But the plot of the ratios between the oxygen and the carbon stable isotopes shows a correlation between the recorded values. But this is less likely to be the genetic indication because the sampling for the stable isotopes have been done through the well-preserved and the most compact part. And just right in time, this paper showed up, where the correlation between the oxygen and the carbon isotopes have been attributed as a symbiotic relationship between Turritis senchesi and dinoflagellates. I would conclude my talk by presuming that the presence of the photosymbionts within Turritis senchesi would explain its exceptional fast growth rate compared to the other 2 rudist species and the oyster. For the next step, I will be testing the presence of the correlation of the oxygen and the carbon stable isotopes, arguing for the presence or the absence of the photosymbionts in the other 2 rudist species, and comparing them to the oysters as a non-symbiotic control group.